So I'm a psychologist, perceptual psychologist, and I've worked a lot at action perception in strange environments. Microgravity certainly is a strange environment. And what I would like to do is just impress a few things on you that you probably don't know. In normal perception, the visual system deals, when we talk about seeing the world, deals with an underspecification problem. So the image on your retina is not rich enough to be able to deduce the objects in the world out there. So you have to make inferences. You have to figure out what's out there given the visual image. And here's one example how the system does it. It makes use of regularities in the world. And light coming from above is a regularity, and above is a matter of gravity and so on. So here you have two identical images. So the image on the right is just the image on the left turned upside down. And you see what looks concave on the left is convex on the right, and vice versa. So the only thing that has changed here is the gradient from light to dark in the sense that in one case, right, if you assume the light source from above, then the gradient from light to dark should look convex. And now try to assume the light source from below. Can't be done, right? You can't make these things pop out the other way. So try to see this as concave and this as convex. It can't be done. So this built-in assumption that light comes from above is very strong.
Heiko, can you alter that by changing your head position? Looking at it upside down?
By changing my hand?
So if I look at it upside down, which I'm not.
Yeah, that's, let's see, that should work. That should work because, yeah, it should work. It's like we can't do it here, but we've actually done a number of experiments to look just into that question. So here, does it work for you? Does it flip when you do turn upside down? Okay, for some people it doesn't work, and that's because you know that you're upside down. But if you remove that knowledge, the body acts as wind. So if you, where's up in 0G? That's basically the question, right? Here, when you do this is up there or there, we can debate. And since it works for you, I guess you took the image with you. But where's up in 0G? What do you think? So we have lots of recounts of experiences from astronauts. For example, on the International Space Station, you have one module pointing this way, another module pointing that way, and where is there an up and down? Yes, people do want an up and down, right? If there's complete uncertainty about it, and people feel uncomfortable. So usually it's the visual environment that wins. So if you put some lights in, no matter where, if you put some lights on the floor, then people will take that to be up. So then they orient themselves, or when they do their work on the space station, they like to be in a position where the lighter parts are here and the darker parts are there. And now, what happens if somebody comes floating in from the Russian module and he's upside down? Then you realize, oops, what's wrong, right? And you get these funny illusions where all of a sudden the world flips, and or you experience falling or things like that. So the perceptual system is very dependent on gravity, and we have at the same time some odd beliefs about it. So here, for example, is an illustration how cannoneers should adjust their cannons so that they hit a particular target. So the idea was to basically point to point F there, and then the cannonball will drop straight down. So this is the Aristotelian physics, if you will, that was close enough, I guess, for the cannoneers in the 17th, 16th century. So we know that things fall down. We also, and I've done a lot of research on that, we also have internalized a very primitive notion of physics that is very close to medieval physics, which is called impetus theory. So basically, an object acquires an impetus, and then it's slowly used up. So why does a ball, like a bowling ball, eventually stop rolling? Because it's used up the impetus. Why does a cannonball come back down? Well, you give it an impetus to go up, and slowly it's eating up the impetus, and then a new impetus starts to act. So once it's used up, a new one can act, and that's everything wants to be at the center of Earth. So basically everything goes down. And well, once we're at it, I should tell you a little about representational momentum. So a way to figure out how if people actually have internalized these impetus ideas, we can do all kinds of experiments. We present visuals of objects doing this, and they don't look bad. When people quickly have to judge and tell unnatural from natural events and say, is this possible or not? Objects that do this are judged okay. Once you have time to think about it, you figure out what the Newtonian physics is. So another way to get at this, what we've done is we've used what's called representational momentum. So if you see an object move, and then you close your eyes or blank the screen, and you ask people to point to where it disappeared. Where was it when it disappeared? They point into the future, right? They anticipate where it will be. So they make an error in this direction. Now if you ask people to wait, so here's the object, it disappears, and you ask them to wait a little, and then say, where did it disappear? You see that this error grows a bit. And then something interesting happens. People also add on an error downward. So if you wait for, say, a second until they can respond, first you get an error in the forward direction, and then you get a downward error. So as if there were sort of a trace of this anticipation that things should then fall down. So gravity is very strongly internalized. Here's a famous experiment by Gilles Clément and others that they did on parabolic flights to look into that very question, is how is gravity internalized? And they had people do a number of things. Here you see an astronaut with blindfold on. They had to draw objects, right? If we draw here, if I were to ask you to close your eyes, draw an object, say a square, you'll be able to draw a square. If I ask you to draw a square here, you're able to draw a square. So you know how you're positioned with respect to gravity. Your body knows how heavy your arm is. You factor that in and you can draw a perfect square. Well, what happens in 0G, right? You plunk people in 0G. Well, you have the error, so you make errors in the direction that you would think the error goes. You basically, right, if you have to draw a square like this, your arm is too light, so you don't adjust, so you get this elongated square. Also, what they did is they had people throw an object. So take a ball, right? If I throw a ball at you and I want you to catch it, well, I factor in gravity, so I throw it there, so it takes a parabola and you can catch it. Well, what do they do in 0G? They throw it there and oops, it goes off. It goes off to the ceiling. And the interesting thing is, after about one trial, I have, this is one of my experiments. So after one trial, you notice, oops, it's going the wrong way, so they adjust. So immediately on the second throw, you hit the target. Is that a fair representation? Am I exaggerating?
Yeah, but what is interesting is that there are fast adapters and slow adapters, and we're not a uniform population. So then the question comes, is it of any value to try to measure this beforehand to tailor a training program for the slow adapters?
Yeah, and then so right, we do adapt fairly quickly, but then some people do it quicker than others. And if we want to figure out how that process works, well, we're used to say playing different rackets, right? I can play ping pong and I can play tennis, and it takes me a few shots to get into the right parameter adjustment, so I don't miss hit, but we can do it pretty well for terrestrial things. Here's an experiment that I did to find out whether our perceived up and down influences very basic visual abilities like time to contact judgment. So here's what we've presented people. This is a tunnel, the visual is not very good, but this was a head-mounted display. In this display was a tunnel, and at the end of the tunnel was basically a cube. You could see the surface of the cube with a picture on it, and this cube would come toward you. Then again the screen would blank, and your task was to hit a button on collision. So right, here's the cube, comes at you, it's blanked, and you hit a button when you think it collides. So you have to nail the point of collision, the time to contact. And we presented identical stimuli in two postures, so people would be supine, looking down basically, but seeing the same, they have the same amount of display. And in the other case, they were prone on the backs. Did I get those wrong? Yes. Supine and prone. And when you again have very short time to contacts, then there's no difference between the condition. But if the occlusion time is a second or more, you get the expected difference between the contact time. So if you are in this position, you expect this to collide a little later, as if gravity were to pull it down. And if you're in this position, you click a little earlier because you think, well, it should accelerate. So we can demonstrate that gravity is internalized here and is at work. So we do factor that in. So that needs to be reckoned with when making. This was the data from the representational momentum experiments. And now another experiment I would like to mention is one I did when I was a postdoc in Larry's lab here, and that's to figure out how well we adapt. So the context there was, well, if we were going to Mars, or if we want to stay healthy even on the moon, we need artificial gravity, so we need to be in a rotating environment. And in such an environment, very interesting and strange things happen, right? So because you're in a rotating environment, say you want to pour yourself a cup of coffee, or when you're here in the rotating spacecraft, you pour your coffee, you actually overshoot this way. So you learn that coffee goes in there when you pour here. Well, if you turn around, you basically you reverse the direction of the adjustment, so you have to pour right in the other, shift the cup in the other direction. So this is really interesting because such an adaptive process does not exist on the ground, right? We have, gravity is never location specific. Right? Gravity is the same no matter whether I'm in New York or in Boston or in Berlin for that matter. It changes very little. When I climb up on a mountain, yes, there is a little less, right? But it's not noticeable. In a rotating environment, the forces basically acting on moving objects depend on where you are in this environment, how far away you are from the hub, and which way you're facing. So you have a problem that's a lot more complex than anything we get on the ground. So we can usually adapt to one parameter change, longer racket, or even some Coriolis force in one direction. So we can learn to pour T when we're at a particular point. So in the space station, a rotating space station, we can learn to pour T, no problem. But can we learn to pour it in all kinds of orientations? The news there is really frustrating. We can't. So what we've done is we have tried to study context-specific aspects of adaptation. So we've taken people and adapted them on a centrifuge, small radius rotating bay, basically, the manned vehicle lab centrifuge here in the Arastro building. And they were making head movements in one quadrant. So they were on their backs, head at the center of rotation. I may have a picture there. Well, I guess I have one where people sit up, but it doesn't, either way, it works for sitting up as well. So you make a head turn and you get this enormous response. You feel like you're rotating, you're tumbling, you get very nauseous after a while. And so you have a very strong reaction. You get eye movements that basically try to correct for the movement that you feel just because you're stimulating the inner ear. So it's a very dramatic effect. And as you make head movements, after a while all those sensations subside. You get very well adapted to it. So the system knows, okay, there's no need to think that you've somersaulted. It's fine. I just made a head turn. So this is people adapt. So then we took these people who were very well adapted to making these head turns on the centrifuge and didn't have any response anymore, and took them into the rotating room at Brandeis University. There's a beautiful lab that has a room, well, half as big as this. The whole thing rotates, and they have people live there and work and things like that. But so we put people well adapted in this moving room, put them in a spot where the forces on the inner ear would be the same. Had them make head movements, similar head movements. So the external environment was completely different. The context, so the visual context, the cognitively, they knew they were in a different spot. Everything was different, and the room looked stable, but they were in a different room. Well, the adaptation held. It was upheld. The head movements in this direction were adapted. They have no response, basically, like somersaulting. And then we had them make a head turn in the opposite direction. So same place, same rotation axis, but just the opposite direction. And they had all the symptoms all over again. And no matter whether we did that in the Brandeis room or on the centrifuge, the MIT centrifuge. So adaptation was extremely specific to not only one axis of head rotation in this case, but also just the direction. And it seems that any adaptation that's one-dimensional, people can handle very well. They adapt to quickly, more others quicker than others. But for complex adaptation to a novel environment where the g-forces are different is really, really hard to learn and to condition. This here is data from what people feel to be their posture. So they're actually sitting 100% vertical on this centrifuge. It's rotating, and they feel, since they're, the center of rotation center of rotation is behind the person, and they feel that they're tilted forward, and you can see that some people feel tilted up to 40 degrees and others only up to 10 degrees. So the individual response is very different, but everybody feels what is predicted by the vector addition of the centrifugal force and Earth gravity, and which is in this case, I think, 30 degrees. So this is showing nicely how the system, perceptual system, integrates information from the inner ear and tactile senses, and maybe even some cognitive senses. Some people are more relying on their tactile cues and say, okay, I'm sitting straight, upright, and others are listening more to it, and you were giving that more weight. There's quite a bit of variability. So in zero-G experiments, as they pertain to artificial gravity adaptation, is happening very quickly, but it's also very, very difficult to achieve complex adaptation.